Hi, everybody. And today, we're going to talk about functional programming in the context, of course, of front-end development. So I'm Henri, and I'm the co-founder of OK Contract, which is a startup which does front-end automation for blockchains. And somehow I won't talk about blockchains at all today, but there's a link. And the link is that when you do blockchains, there's a lot of things that happen in the client, in the front end. And because there are less servers, because we want to decentralize as much as possible the infrastructure, so the client itself is responsible for managing dozens and dozens of connections, asynchronous calls, gathering bits of data, recomputing everything locally in the client. And because of that, the blockchain clients are extremely complex. And we struggle with the complexity. And, I have often this joke just to get started is, people often, they talk about backend, and they say, oh, yeah, we're doing this and that, and it's super complicated. And, oh, you guys, you just do the front end, that's one thing. Whoever lived this? Like, oh, you're doing the front end, it's so easy. Yeah, it's too easy. What's happening?
Okay. Oh.
No, yeah. Okay. No, okay. But indeed, when you look at what is exactly happening inside those applications, it can be extremely complex. And even more complex than backends, because backends, you split the components pretty well in your architecture. You have tons of different servers doing different things. But when you are building your front-end artifact, usually there's everything in it. And so it's more complex, especially when you take in account that there's a lot of asynchronous calls and asynchronous data to manage, and you want to do this in an optimal way. And the problem is, I'll go straight to it, state management is pretty hard to get right. And we think that functional and reactive can help here. So just to make the definitions clear, and I know that several of you know functional programming, basically one of the main aspects of functional programming is that the values are immutable. So for instance, if you define a list U, basically it will never change. What you can do is you can construct V, which prepends 9 to that list, but V is a separate value which starts with 9 and then points to U as a list and construct the append list. By the way, who knows what syntax is this? Close. It's unctional. And it's just that it's one language which has a longer history on programming the web with unctional, and I did that part. I was the author of a framework called OPA, and the OPA compiler, basically 15 years back. But also what OPA didn't have is reactive programming. And reactive programming is the way basically to manage asynchronous data streams. And basically, instead of accessing values directly, you use an indirection where you subscribe to values, and then the values can change. So if you are into semantics of programming languages, of course, that should ring a bell, and you could say, oh, maybe we can represent this as monads, which are a way basically to encapsulate computations as values with primary two operators, so return to create a monad and bind to combine it. And you'd be right, and it's probably the right formalism, and there's still a lot of research that we can do in that area. Also, I'd like to quote this guy. I saw him on Hacker News with an article in the last few days. And that guy says, basically, the functional people programming can be quite smug, and sorry for that, but they're often right. So I hope that it's the case. So getting back to it, when we talk about reactive functional programming, most often we are talking about a research paper which dates back from 1997 by Elliott and Hudak, and which is FRP, functional reactive programming, and which is something which is extremely well specified. Basically, it introduced what is called behaviors for continuous change, and that is a value which is a function of time, and that changes over time. And then you can have events, which are pairs basically between a time and a value, or a change of the value for discrete occurrences. And there's a reason why they did this, is because at the time they wanted to do animations. And so you have something pre-programmed in the animation, and then that's what the user does, which changes the course of it. And this is why you have these behaviors and events. And then you have a pretty complex library of functions, which we call combinators, to manipulate and combine these different behaviors and events. And that leads, for instance, to one library framework that some of you may know, which is RxJS. So basically, it's based on observables for behaviors and observers who watch the behaviors. And then you can have a lot of combinators basically to introduce the events. And there's basically a whole library, even graphic references on how you can combine these different operators. The problem with RxJS is it's a bit complicated. But there is a bit, another form which is quite popular of functional programming. Can you guess which one? Yeah? And spreadsheets. This is functional programming as well. But this is functional programming without telling it, so many people like to love it. And this was not unnoticed, because, for instance, if you look at MobX, which I'm sure plenty of you know, in their own documentation, they say, oh, using observable is like turning a property of an object into a spreadsheet cell. So they get the reference right. But in my opinion, the problem with MobX is when you look at the implementation, everything which was nice and functional has gone away. And basically, it becomes extremely object-oriented, extremely imperative-style programming. And because of that, it's verbose, and you're losing a lot of the nice properties that comes from functional programming. So this is why we started, in fact, a new minimal library, which we call cells, in reference to spreadsheet, obviously, and which we try to be a very pure form of spreadsheet, but without the UI. So it's a non-UI library that just does computations in a functional way. So it's MIT licensed, and we will never do a business for this. You can just use it as you want. And it's less than 10 kilobytes, minified gzip. And we really intend to be that way, like we now have a 500-byte budget to add more features. It lies on two primitives. So there are two types of cells. The first type of cells is what we call a value cell. It's a value that you define with an initial value, and you can change whenever you want. And you also have what we call a map cell, and which is a computed cell, which is computed over other cells, which could be either value cells or map cells. And basically, you can set or reset the value of value cells, and the map cells will be recomputed, but they will never be redefined. They're immutable. How do we use it? So you just import sheet, which creates, basically, it's your object to create a new sheet. It's a new spreadsheet. Usually, you want one per application. And you can create as many cells as you want. It's not a 2D UI where you have rows and columns. It's a graph, basically. So it's a spreadsheet computing library in a graph. And you can create as many cells as you want. And you can create as well cells with promise. They are completely abstracted. And they are even abstracted in the map cells. So when you call, for instance, sheet.map, you are going to call, for instance, the function AB gives A plus B on cell A and cell B, and it will be automatically recomputed as cell A or cell B change their values, whether they are value cell that you set manually or they are already computed cells. And if you have a long computation, for instance, you're fetching some data from an URL, basically, you don't need to have a sync, you don't need to wait for them, everything will be handled automatically in the computing library. So how do you get access to values? So as we've seen previously, all definitions are synchronous. When you define values, when you define computations, it's synchronous. But because you're just defining the computations, they're monads. So you're not getting the immediate computation. This will be done later. So basically, you wait when you want to get a value. When you want to get a cell, you just await cell.get. You can access the immediate value. For very rare case, it might be renamed using .value. But more often, what you want is just to subscribe and basically create a subscriber which will react to the changes of that cell. And that leads basically to building a compute graph. When you define all your cells, whether they're value cells or map cells, basically you're building a graph of all the computations that will happen in your app when your app is running. And you define this graph beforehand, and then basically at runtime, you just run it. So at any given time, this graph gives a functional program. It's very easy basically to add new definitions or to transform or to add new definitions, but transformations, of existing cells is never allowed. It's immutable. And memory management is something that I will dig in because it's semi-automatic, and we can't do more. So you can delete a cell manually if you want with its subgraph, possibly. But we have a feature that I'll present just next of proxies that automate the deletions of subgraphs, basically, which are attached, for instance, to a graphical component. And we also have garbage collection, but it's explicit. Like you have, when you're building the library function mostly, you can explicitly tell that you don't need a cell anymore, so it will be garbage collected. So let's see how proxies work. So basically, they are automated memory management for these subgraphs. So what you do is you just create a new proxy for a sheet, and all new cell that you will create will be attached to that proxy. And when you leave, you can call proxy.destroy, which cleanly destroys the whole subgraph. So when you have components, for instance, and I'll show you Svelte components or React components, it's very easy to create a proxy when you create your component, have all your local cells, and then destroy the proxy when you destroy or unmount the component. So if you've seen here the compute graph, which I've shown previously, there are some dashed lines. And those dashed lines are very important because it's the core feature which enables this to be very practical. And this feature is pointers. As long as you keep everything purely functional, there will be limitations. But what opens completely the scope of everything you do in a simple way is that we manage pointers. So basically, you can have a map cell whose definition is another cell. So basically, you could have, for instance, condition, and depending on condition, the pointer cell is cell A or cell B. And this gives you very easily all the flexibility you need basically to do very complex application. And I can tell you this is where most of the research into building cells itself went, because if you don't have pointers, it's quite easy to implement. If you add pointers, then it requires new research on the runtime, and it's basically something that we could publish in functional programming research conferences. One thing which is very practical is we chose to implement the Svelte store interface. So basically, you can use cells just as they were Svelte stores. So you can use $cell, for instance, to create a subscription automatically in your Svelte templates, or you can even use $cell equals value to set a value cell. And we'll be releasing a lot of libraries. I'll show some of them in conclusion. So what I wanted to insist on as well is when you have multiple libraries that use cells, they can communicate extremely well between each other because the cells become somehow an API to exchange data and computations between libraries. And this is very important because this is the level of interaction that we often lack. Remember when I showed my first graph? I said, oh, front end is just a single square in your infrastructure. The problem is when you have a lot of different libraries, how do they communicate between each other? It requires a lot of glue code always. But if these different libraries use cells, you can connect them extremely easily because they are the same data flow. So, time for a demo. And this demo is based, of course, on Svelte. I'll try to zoom in. So here, it's a very simple app where we're using a site called dog SEO, which basically gives you random images of dogs. So you can like or dislike. If you like, it's added to the queue, and it fetches a new dog. So basically, you see, do you like or do you dislike that one? Like. Okay, like was the... Oh, okay, dislike. If you dislike just because you have another one, and then, okay. And basically, it will always fetch a new dog. So this is a JSON API. And then we need to fetch the JSON, fetch the data, which is shown as well, because the breed here is a Malamute. I didn't know that one. Did you know? No, I didn't. But if you like, for instance, then you have another one, which is a Weimaraner, etc., etc. So this app, I will show you the limit, is just, it's mostly one file. It's just the image component with the, you know, the nice loader, which is a separate one. And it's extremely simple. For instance, the function to fetch is just the native HTML fetch API. And we can also simulate a failure. If I fail, oh, error, no internet. It comes here. It's a rejected promise. But when I refresh, then it starts again with a poodle. And here, if you look at this code, it's completely straightforward. So I say the response is basically the fetch dog function. And then I map getDog URL, and everything is asynchronous here. You know, if I had to code this manually, there's async everywhere, but you don't see them. You just define your computation without a single async. You don't care at all about this. And then, if you use Svelte, you just use your subscription, and you just show the $URL, $breed, etc., and everything just works with no code. If you look at the import, it's just OK contract cells and the Svelte REPL. There's nothing. It's just less than 10K library, and it removes most of the boilerplate code that you usually write. So let's getting back to a few slides. It works with React as well. And it's not limited to Svelte at all. And we have this use cell hook, basically, and for instance, this is an actual sample of our React SDK. Basically, you define your cells and you use whatever cells that you want to present in your interface. You can omit the intermediary cells. The intermediary computations, you can just leave them to cells and not show them in your React UI. And this is the complete implementation of the use cell hook. It's almost nothing. It's almost empty. Because the only thing that you need to do is subscribe, and basically when you subscribe, you set the value of your React value. There's almost nothing. And it works most probably as well with other frameworks the same way. Another thing I wanted to show you is it's 9.5 kilobytes, including debugging. And here I want to show you another quick demo. And when you zoom Chrome, you lose the tabs, right? How do I zoom out? No. How can I zoom out this? Yeah, now it's done. Yeah, okay. Yeah, here. Okay, so another demo. This one is running locally. And it's a to-do MVC, where you can basically do two things. So here you can see, these are all the cells which are defined for my to-do app. So I can add foo, for instance, And then you see, oh, foo has been added to my graph, and I can compute the live graph of all my cells. So I can add bar as well. Let me add bar. Okay, and now you see I have this foo and bar, and they are sorted. There is an intermediary representation for the sort, and then it's sorted, because if I say that bar is done, I say bar is done, and basically it's sorted. It goes to the bottom of the list. But if I uncheck bar, then it goes back to the top. And there's also a hash which is displayed here, which changes when I select another thing. And it's just an example to show that I can have a current selection. And you see the dashed line here. It basically means that here I have a pointer, and here I have a pointer as well. And for instance, the selection is a pointer. It's extremely easy. My selection is just a pointer to the cell that I can pass as a prop to, for instance, my Svelte or React component, and you will have the whole access to the cell itself where you can do anything. If it's a value cell, you can sell its value, and everything will react automatically. You don't need to care about the way you propagate changes. So it's really magical. And as well, we have this. Let me zoom in. So we have also 9.5 kilobytes. There is an injected debugger. So you can ask for the help. It says, oh, this is where basically you can generate the graph.graph, et cetera, et cetera. You can see, for instance, what is the cell number, let's say 2. I don't know which one. Oh, cell number 2 is the hash. It depends on cell number 1. Nobody depends on it. And this is its current value. So basically, it's super easy to debug all your computation by accessing the values directly. Okay. There's also a standard library to manage arrays and objects like filter, reduce, sort, etc., etc. And all this is, again, included in the 9.5 kilobytes. Debugging, this you've seen. And just as a conclusion, I'm on time or? Okay.
When you ask
30 seconds.
The answer always no time.
Okay, 30 seconds. So we use it in real life to build our SDK and the OK Contract Hub. And it's an extremely complex application because it's a blockchain application. We use libp2p basically to create a peer-to-peer network. We connect to random nodes using the peer-to-peer network. We also connect to the blockchain nodes directly, which themselves are decentralized. So we are connecting to maybe like 50 servers to serve this UI, and 50 random servers. And there's a lot of computation which is happening as well. We have to decode, we have to verify crypto signatures, etc., etc., etc. So for this, we use 5K cells, and it's working way faster than what we initially implemented manually. And this is how I will conclude the talk, is because when you think about it, when you code manually, what happens is you think that you organize your code in functions, you organize your code in modules, but when it's asynchronous, you begin to wait for one event. And maybe because you're waiting here, unless you're using workers properly, which maybe you aren't, then you are suboptimal. Versus here, we compute a whole graph of everything. And every bit of data or every bit of asynchronous computation that comes then does an optimal way of recomputing the next wave of data until you have everything you want in your app. So I really think it's a life changer. So the links are github.com okcontract/cells. Several libraries are on the way. We're also building UI components based on cells. The demos that have shown the to-do and the dogs demo are here. And of course, yeah, if you want to, you can follow me on X. So I'm Henri Dash.
Thank you.
Dash, okay.
Thank you.
And OK Contract.
I have to say that's more than 30 seconds, but I forgive you because you're nice talking.